enzymes. That's what we're looking at. Enzymes are a function of proteins that are one of the most studied things in biochemistry, and one of the first things that we really kind of looked at. And so enzymes are essentially catalysts to reactions that happen inside the body. Okay? And so what does a catalyst do? Okay? It makes the reactions reach equilibrium faster. So it makes the equilibrium go faster, and so effectively it looks like the rate of production of product becomes much quicker than if it were not catalyzed. And so you can get higher reaction rates, 10 to the 6th, 10 to the 12th times greater. Reactions can happen under milder conditions, and reactions happen with much greater specificity. Rarely is there a side product in the organic chemistry that happens inside the body, not the same thing that happens inside an organic flask, in which you only get 40% because there's so many other ways for those two molecules or the reaction to occur that you get undesired products. It doesn't mean that in organic chemistry the reaction doesn't go to 100%. Usually you use up 100% of the reactant. You just get only 40% of the product that you want. You get all sorts of other products that are undesirable. That doesn't happen within the biological system. Okay? Enzymes are composed and can be proteins alone. Not often are they always proteins alone. Most of the time, a protein is helped in the reaction by having some sort of group there, either a metal ion or organic molecule. The thing that is not peptide that helps in the reaction are called cofactors, prosthetic groups, or coenzymes. And so a protein that has the protein in whatever cofactor it needs is called the holoenzyme, and the protein without its required cofactor is called the apoenzyme. You saw those terms when we talked about when we looked at the lysozyme. Okay? Enzymes for a long time were believed to be only protein-based. We now know that there are RNA enzymes, and so we'll talk about some of those in later chapters. Enzymes have a whole different nomenclature for things. In general chemistry, we've told a chemical story. We start off with once upon a time there are chemical reactants, and then happily ever after there are products. Okay? Just to confuse you, we do not have reactants in biochemistry. We have what are called substrates. Okay? So the reactant is now called a substrate, and it is a substrate because the reaction that occurs happens inside an enzyme, so the enzyme must bind to that reactant, and so the fact that it is the starting material that must be bound converts into a substrate. And once that substrate is inside and bound to the enzyme, the chemical transformation can happen. Now, it binds into a pocket that is usually called a specificity pocket. I am specifically binding one reactant. Okay? The reaction occurs at the catalytic portion of the protein, which is called the active site. And so the active site has next to it or incorporated into it a specificity portion and a catalytic portion. The active site and the specificity site are very small numbers of amino acids in the entire protein. And so you may have hundreds of amino acids in that protein. They are there to keep the key 10 amino acids that bind the substrate and catalyze the reaction and places them in three-dimensional structure. Now, that doesn't go to say that the rest of the protein is not functional. The rest of the protein may have binding pockets that bind it to a certain place, so organizational. Or the rest of the molecule may have other binding pockets that will bind regulatory action and either turns the protein on or turns the protein off or modulates its effectiveness. And so, but the actual reaction is a very small segment or number of side chains of the primary sequence. The active sites create a unique microenvironment. This is how I can do an organic reaction inside a aqueous solution. Once the substrate binds, it can exclude water. And so inside the protein, it can be truly as organic as any of your solvents are, an organic solvent. And so you can have an organic reaction occur. How do the enzymes work? Well, the reaction rate is based upon three things. How often the substrates that are reacting collide together, how much energy is in the collision itself, and the probability factor that they collide in the right orientation for the reaction to occur. The enzyme will affect all three of these. Okay? How often they collide, with what energy it collides, and its probability factor in terms of orientation. Okay? It enhances the probability factor because what you do is you bring the reactants immediately close together. Okay? And so the probability factor is bringing them close together, and when they are bound in a unique three-dimensional position such that the two areas that are going to react are lined up in perfect orientation for the reaction to occur. In an organic flask, a round bottom flask, the two substrates are floating around and they bang against each other. Okay? Sometimes they bang in a way that they're oriented to cause the reaction to occur. Sometimes they bang together in not a way to get the reaction that you want to occur. But sometimes they bang in the wrong direction and you get a wrong product. Here, everything is aligned so that when the reaction occurs, it only proceeds towards one outcome. So, probability factor is increased. And so, some nomenclature. E is what? S is substrate. The ES complex is an enzyme plus a substrate that are complex together. What's P? Product. So the enzyme holds onto the substrate, a reaction occurs, the enzyme is now holding onto product, and then the enzyme has to let it go. Okay. It lowers the energy factor. Okay. Whenever you have a reaction, okay, something coming together, you go from the two lowest energy states of the two reactants, and then as you progress through the reaction, you go through a high energy state, a barrier. That barrier is called the transition state. Sometimes that transition state is really high. So in organic chemistry, you reflux it at a higher temperature. You give it more temperature, it can go past that transition state to product. Well, here's what we don't do in the body. We don't heat ourselves up to make the reactions go any faster. Okay? But what we do is we stabilize that transition state. We make a balance to that bad energy state to make it lower. So, let's say you have a neutral molecule coming together. They react. In the middle of the reaction, you create a negative charge. Neutrals are much better than having charge. The negative charge somewhere in the middle of that transition is high in energy. Okay? I would need lots of energy to get through that negative charge. That's temporary. Well, in the enzyme, if you create a negative charge as part of the transition state, what the enzyme will do is put a positively charged residue right next to where that negative charge is going to be formed. If you have a positive residue next to that negative residue, you get stabilization of that, what would be a bad interaction, now having stabilized during that transition state. That lowers the overall reaction. And so we're going to stabilize one and only one transition. This leads to one and only one product. Also, the enzyme will increase the collision factor. If you have to have two things coming together to react, Well, if you bind your two things that are reacting inside the enzyme, basically you get a container that has only two things, and the concentration becomes infinite because there's not dissolved by anything. And so the only things it can react with are the things that are bound, and so we increase how often they hit because that's the only thing they can hit. And so we can affect all of the things that control rate, and we increase them. Has anybody ever seen one of these? An energy progression through a reaction. All right, we start at the enzyme and the substrate, that's cool. And then we have the enzyme and the product. If it is uncatalyzed, the substrate to product goes through a transition state that is very high. Okay? And so it requires a lot of energy, even though, take a look, the delta G is negative. The product is a whole lot more stable than the substrate, the reactant. We said that that is spontaneous, right? Can be spontaneous. All right? I can put a log on the top of this desk, and that log, being converted into CO2 and water, will release a lot of delta negative G. But if I set that log on that desk and I let it sit for hundreds of years, will it combust spontaneously? No, but its delta G is huge. Okay, what has to happen? I have to get it past the activation energy a little bit so that it can provide energy for the rest of it to go. So if I provide a flame initially to get the first started, then as more of it progresses, more energy is introduced, I can get more on, and I can produce lots and lots of energy, exothermic energy, by burning the log. But I have to get through the transition state. All right. Now, the enzyme does this. It lowers that transition state. So now the transition state is not here, it's here. A lot less energy. Okay. Now, do you see that transition state? It was one big energy transfer, right? What happens in the catalyzed reaction? What are you seeing? One? No, you see multiple humps. Okay. What you see is there is usually, sometimes you can't see this, this is an idealized case, okay? There is an energy necessary to get it bound. So some sort of energy necessary for the substrate to actually bind in there, okay? The highest energy is the reaction, the transition state itself. And then there is some sort of energy to release the product. Sometimes you can actually articulate and see all of those energy states. Most of the time, though, what you see is just a lower energy state. That's what you normally see. Even though we know fundamentally there's some energy to bind it, there's some energy to release it, it's really what we're dealing with is the highest energy state of that transition is what governs the overall rate. Delta G negative is favorable. Okay, but the transition state is what really relates to the rate of reaction. And so we need to lower that transition state, the energy necessary to go through the transition. The enzyme alters that. Okay, and so if you take a look at that figure at the bottom, with no enzyme, if it's a stick, the transition state is bending that stick till it breaks, and then the product is a broken stick. So you can see it requires a lot of input of energy to break a stick. Okay. Now, the enzyme is going to change that. We'll see another slide in just a moment to change that issue. So we have substrates that bind into the enzyme. The enzyme will create an ES complex. The ES complex is very important for the reaction. Now let's think about all the things that have to happen for an ES complex to form. All right. So I can do this. The substrate, the enzyme and the substrate come together. There is a constant rate for binding to the ES complex. Okay. Now there are a couple things that can happen here. I can convert this into product and release, and there's a rate for that. Or I can just let go of the substrate and come back to this, and there's a rate for that. There is also a rate that is little tiny. I can take a product, put it in the enzyme, and go backwards. Most of the time, this is so little that essentially it's zero. Okay? So what we really have to do is we have to talk about the rate to its form, the rate where it just falls back and nothing has happened, and the rate in which product is produced. There are 3 different rates that govern, most of the time, how much ES complex is there. Remember, the ES complex is the reason the reaction can happen. So, governing or understanding how much substrate is bound to enzyme is going to be our fundamental important thing about thinking about enzymes. The active site here, if you take a look at it, you can see where the substrate is going to bind. Okay? There's a kind of a valley right in here. Okay? The reaction occurs right here. Those 2 amino acid side chains are going to facilitate the reaction. Right here is where the specificity happens. Why a substrate will actually bind. If you take a look at this entire 129 amino acid protein, 6 amino acids of the 129 are part of the reaction, both binding, specificity, and catalytic reaction. The active site is a very, very small portion. Although one thing that is common to an active site, it is some sort of crevice or pocket that is accessible to the surface. Okay? So the active site has to be accessible to the surface because your substrate is floating around and it has to bind into the enzyme, and so it has to be at least accessible. All right, the cleft, the crevice, the pocket, wherever it binds. And once that substrate binds in there, you have a unique environment, such that the pKa's can even change. It isn't now the same solution. It's not in the same solution environment once the substrate is bound. So sometimes pKa's are a little bit different inside the active site than when we are inside the cytosol itself. All right. Now, how is that ES complex or the active site arranged? Well, see that stick? We want to bind to it. Remember, and we want to bend it and we want to break it. Well, if I have an enzyme that is perfectly aligned to that stick, the stick will bind very tightly. Okay? But no reaction occurs. Why is there no reaction occurring in this picture? I bound to my substrate, and I said substrate and substrate bound to the enzyme is going to cause a reaction, but in this picture, no reaction occurs. It is an issue of free energy. What was that? Yeah, the ES complex is lower than the products. Why is the ES complex lower than the product? What is it?
It's too stable to react.
It's too stable to react. Okay, so what happened in this particular enzyme? It is not a good enzyme. It is a good binding molecule to the stick. It stabilizes the stick shape. But that's not the product. What's the product? A broken stick, right? And to get to the broken stick, you have to get through a bending. Is that going to bend? No, it is stabilized in the straight form. Okay? So an enzyme cannot be a perfect match to your substrate. It can't. Because if it is, it's just going to stabilize the substrate structure. I don't want that. What is the difference here? What is the enzyme shape going to stabilize most? the bent shape, right? The transition state. The enzyme has the greatest stabilization or the greatest interaction with the transition state. Now, remember we have to have some specificity. Right here and right here bind very well to the stick. And I have to be able to attract it, right? But I am not stabilizing the entire structure of the stick. I attract part of it, and I stabilize the transition the best, so that it makes it easier to get to that tension point, and then once it breaks, well, take a look at the end. Does that shape really want to bind the product anymore? No, the products now can move around and they can fall away. I want to have some affinity to the substrate. I want to have no affinity to the product, and I want to have the best affinity to the transition state. That makes a good enzyme. Now the active site, there are two models. Here is a model or a picture of what's called a lock and key model. The crevice or the pocket for the substrate coming in is perfectly aligned to the substrate. So it's perfectly able to bind in there. Okay? That is one idea about how ES complexes are formed. Here's a second. It's called an induced fit. Now look at this picture. Does this shape look like that substrate? No. Oh, come on. Stop. Did the animation work? No, go. Animation, please work. There it is. So the substrate comes in, and as it binds, if you take a look, it dynamically moves to make a better binding, and it induces the fit. Whatever binds induces a better fit, makes the protein move. Okay? And so there are two competing ideas, probably a mixture of both, not one or the other, although you can see very good example of induced fit. You find very good examples of lock and key, but it's kind of like a covalent bond and an ionic bond are two extremes where most of them are polar covalent, somewhere in the middle. All right. So, how fast can the reaction go? All right. In the presence of an enzyme, there are lots of different reaction rates or velocities that are observed. Okay. And if you vary the concentration of the substrate versus a constant concentration of enzyme, you will find that you get different speeds of the reaction. Okay. But what you're going to find is you're going to get a certain concentration versus that enzyme that will create a maximum rate that the enzyme will work. All right. When the maximum velocity has been reached, this is what is actually happening. There is so much substrate in the solution that at any moment, the enzyme will be completely filled with substrate. Meaning, gets substrate, produces product, kicks it out, but immediately it picks up substrate again. And every time it releases product, it picks up substrate again. At that time, you are measuring the maximal velocity of that particular enzyme. Okay? And so, here is what the enzymatic function looks like. At low concentrations of substrate, okay, down in here, little bit of substrate, you look at how fast the reaction is being produced. And so here you plot concentration, here you plot concentration of product versus a time period, how fast it is. Sometimes you will also be given per milligram or a amount of enzyme. If you don't have in that unit up there how much enzyme it is, that is one thing that is constant throughout. Okay, so sometimes they articulate it here, sometimes they do not, but you will always know that the enzyme concentration is the same. So if down here, if I take substrate and I double the amount of substrate, the velocity will double. There is a point at which it's linear. I double how much substrate, I double the product formation. But that doesn't continue. All of a sudden, it will start to peter off, and I will get to, it doesn't matter if I double the concentration of substrate, I will get no faster velocity. And so I reach what's called Vmax, or the velocity that is maximal. All right. This is what's called the kinetics of a Michaelis-Menten type of enzyme. Michaelis-Menten is the two responsible for the derivation of the equation that governs this. This looks like, but it is not, a hyperbolic function. It's similar to, but it's got its own math involved. Okay, so at the beginning, the velocity looks linear, although it doesn't continue to be linear, and there's some point at which we get a Vmax. All right. So we're going to start looking at the Michaelis-Menten equation. Now I come back to this. All right. You start off this. You put a test tube. You put in some sort of enzyme. You put in a milligram. All right. And then you put in some sort of substrate, a concentration, 1 millimole. And then you start measuring the product. To get the product, remember we had to get to the ES complex. And the ES complex is governed by how fast it binds, how fast it dissociates, and how fast it converts to product. Okay? The actual velocity, how much product is made, is dependent upon only one thing, K2 times the ES complex. Because that rate is the only one that produces product. Okay, so if I take the rate times its concentration, I can find out how fast or how much product is being produced. Velocity 0 is the initial, and then velocity max is when we get to the fastest it can be. All right. Velocity of any reaction is the rate constant of the step times the concentration of reactants. So that's where we get K2 times ES complex. Now, so to do this math, what I really need to know is the ES complex concentration. It's a little bit harder to get to. Okay. So what is the ES complex? Okay. What does that statement right there say? What was the first word? Assume. Okay. We're making an assumption. Okay, so all of the math and everything that we do is based upon this assumption. And it's the assumption called the steady state. Okay. Throughout the majority of the time of the reaction that happens, okay, it doesn't work right when you mix things up. It doesn't work right when there's almost all substrate gone. But through the majority of the reaction, the concentration of the steady state remains constant. It's in a dynamic equilibrium. Okay? It's changing because some of the ES gets converted to EP product, right? But some of the EP, once it releases, becomes E, picks up substrate, and so the ES complex is constant even though it's forming and breaking down, forming and breaking down. I get to a constant concentration. All right? And so, I do know this. I do know how much enzyme I added. This thing. What I really don't know is that thing. Oh, sorry, I take that back. I'm going to take this back real quick. I do know E total, what I added. This I'm not too sure. how much is in the ES complex at any time. And if I take the total minus the ES complex, this is free enzyme. Okay? So to make the ES complex, the rate of it, I take the rate, which is K1, times the concentration of the reactants, the E times the S. Okay. Also, okay, so the E I can substitute into something I know, the enzyme total. Okay, so what I did was I took this E, and I took these two things, and I put it right there. All right. So now, rate 1 times the total amount of enzyme minus the ES, I don't know, times the substrate. I know E total and I know ES. I'm sorry, E total and I know S. The only thing I don't know is the ES. That's what I'm looking for. The rate of breakdown is the ES complex times the rate of K minus 1 plus the K2 times ES. So the rate of the formation is that first thing, and the rate of breakdown is the other. Steady state means that those two rates have to be equal. That's where my assumption is, where my math works in. So I can make them equal to themselves. Now it gets nasty. Okay? I got lots of stuff. And oh no, I didn't put this as a prereq, but I thought algebra should probably be a prereq to this course. Okay? So, we're going to distribute. So what in the world do we distribute? Well, I've got this parentheses right here, so I got to distribute K1 times S to all of those on the inside. So I've distributed that. Now it gets a mess, right? But what do you see all over the place?
E's and S's.
E's and S's, right? E's and S's and all, it just looks like a mess. What we're going to try to do is get ES together, because that's what I'm trying to look for. Okay? Now, I've got to add K1 ESS to both sides, because I got a negative on one side. I don't want to do that. I want to have everything positive. And what that also does is, here's an ES, there's an ES, everywhere an ESS. Okay? And so I now have all the ES's on one side of the equal sign. I'm trying to combine them. The fact that I put all the ES's on one side, I can factor out anything that is not ES, and I made it just a tad simpler. Not so much. But then I divide by what I factored out, and I get ES is equal to all that crap. Okay? You see that? All right. ES, I'm getting to it. All right. That's all I can show you. All right, I've run out of time. Now, this derivation is not something I'm going to ask you to reproduce. Okay? But I do want you to understand the fundamentals of why the math works out. I will make you know what a steady state is, and I will make you know what the outcome, the final equation is. All right, but I do want to walk through the steps as we go.